Hi, chemists. Today is Wednesday, April 1st. Happy April Fool's Day. We still have chemistry. That's the joke. So I am going to share my screen. I'm glad that you're here. And let's get to work. So we're still working on the same standard. It is about the factors that are affecting reactions. Our objective for today is I can define chemical equilibrium and use Le Chatelier's principle to predict how changes in pressure, concentration, and temperature affect systems in equilibrium through doing an activity, taking notes, watching videos, and performing practice questions. So the only thing that should be new in all of this is the word equilibrium in Le Chatelier's, which I'm sure I'm butchering that. I'm not going to pretend that I even know how to speak a little bit of French. But we know what temperature, we know pressure, and we know concentration. So the only foreign thing is, like I said before, the new principle and chemical equilibrium. We're going to talk about that. So first, we have a quick review at the top of your page. I can show you guys just where that is. On the top of page 7 in your packet, you have these 3 questions to just quick review to answer. So pause the video now, answer question 1, 2, 3 on page 7, and then we'll go over them. Okay, welcome back. So by now you should have completed questions 1, 2, 3 on page 7 that are just quick review questions. So first one up is, what is activation energy? How does it look like on a graph? So activation energy is that minimum amount of energy in order to start a reaction, right? So hopefully you guys were able to get this down. So activation energy looks like this. It's that little bump that we see on a graph. So the little hill that we have to get over in order to get from our energy of our reactants to the energy of our products. Question 2, so what are the 4 factors that we discussed that affect reaction rates? So number 1, these can be in any order. They're not, the order doesn't matter. So temperature, concentration, surface area, and presence of a catalyst. And then finally, what is the difference between exothermic and endothermic reactions in terms of energy of reactants and products? So endothermic reactions are absorbing energy, so their products have more energy than their reactants. So it's going to be this first graph right here on our left, whereas exothermic reactions are giving off energy, so they're going to have less energy in the products. So it's going to look like this one on the right. So we have some notes to take. You guys can just follow along throughout a page and a half of notes from page 8 to page 9. So you guys, it's similar to what we did while we were in school. Actually, I'm sorry. We're going to do a quick a quick activity together. So I want us to visualize how products versus reactants are over time. So we are going to make a graph that is going to be time on the x-axis, which is this horizontal axis right here. And then we're going to make amounts, and you guys should be writing this as I write it. Okay, we're not going to add numbers on the y-axis. So that says amount, product, and reactant. So the amount of product versus reactant that we have. So I'm going to do product in red and reactant in, let's do this blue. So remember, reactant is what we're starting with. We're reacting it together. And then product is what we're ending with. So product, we're going to start off with a lot of, and then decrease, because we're using it up in order to make the product, whereas the product is the opposite. So at time, at the beginning of the reaction, which is going to be this our origin over here. So when time is 0, we're going to be bringing up the product to form more product as we use up the reactants, and the reactants are coming products until the amount of products overtakes the amount of reactants. Okay, so I am going to, so this is what you guys should have. So pause the video now if you need to write this down for yourself, draw it down, whatever you got to do. Or if you need to rewind me, or if you don't, that what I said didn't make sense, then ask me questions, okay? So I'm going to clear this. Rewind me if you need to. I'm going to exit out of that so we don't do that. So then you have questions 1, 2, and 3 to answer. So as we were just doing our annotations, after you just made those annotations of the graph, so what do we notice is happening? What happens to our products during chemical equilibrium? And then 3, how can you tell that the reaction has reached chemical equilibrium? So pause the video now to complete questions 1, 2, 3 on page 8, at the top of page 8, and then we'll go over them together before we move on. So welcome back. So by now you should have completed questions 1, 2, and 3 on page 8 of your packet. So we're going to go over them really quickly. So question 1, what happens to reactants during a chemical equilibrium? So the reactants start off high, like a high amount of reactants, and then they go down as the reaction progresses because you're using up the reactants to create products. So that leads into question 2. So products start off as a low amount, and then they get higher as you're creating more product with the reaction. 3, how can you tell that the reaction has reached chemical equilibrium? So this one is kind of tricky. So equilibrium means it's reaching like a steady state. And this is what we're going to talk about today. So I don't expect you guys to know this, but you can tell that when the amount of product and reactant start to reach a constant level. They don't necessarily have to be the same, but they're just constant. So they start forming horizontal, like flat lines, meaning that they're staying the same over time. Okay, so now we're going to go into your guys' note-taking portion of this packet. I know it looks like a lot, but it's a lot of fill in the blank. So all of the blank words you should be typing in or writing out, depending on how you take notes. And then all the underlined words are going to be the blank space in the PowerPoint that we're going to go over. So I'm going to start that now. So equilibrium is the balance of our forward and backwards reactions. Reactions can both proceed in a both forward and a backward direction. The forward reaction is what's going to use the reactants to make product. Backwards reaction uses product to make reactants. So it's just literally the same reaction, just going backward. So our reactants here would be SO2 and then O2. And then this is supposed to be an arrow moving to SO3. So that's our forward reaction. And then our backward reaction would be using SO2 to make O2 and SO2. We're using SO3, I'm sorry. So eventually these reactions are going to balance out, and when they do balance out, that's called their chemical equilibrium, where the forward rate is equal to the reverse rate. So chemical equilibrium only occurs in closed systems, meaning that no materials are leaking out into the environment. So we're not losing any of our molecules. So this would be in a balloon, if we had a closed balloon, if we had something with a lid on top of it, just we're not losing any of our product, because then that would just make it keep going in the forward direction. So the amounts of products and reactants are always going to stay constant once we reach this equilibrium. And like I said, they're not necessarily going to be the exact same. So this is a dynamic process, meaning it's ever changing. It's not stable, meaning it's not always going to be just the same, but the amount of product and reactants is constant. So now we have Le Chatelier's principle. So there are 3 factors that we're going to talk about that will affect a system in equilibrium. And when we say affect a system in equilibrium, that means it's going to shift in one direction or the other. So systems are always going to respond to stress, to change, by trying to reduce the effect. So if we do something that causes it to shift one way, the reaction itself, the system itself, is going to shift in the opposite direction to kind of reduce this stress or change. So the first of these factors is concentration. So if a substance is added to one side, then the equilibrium will shift to the other side to increase the concentration. So the equilibrium always shifts away from what's added. So that is a little mnemonic for you to remember. So the equilibrium is always going to shift away from what's added. And then if a substance is removed from one side, then the equilibrium will shift so that there is less on the other side. So it's going to shift toward what's taking away. Okay, we'll have practice with that at the end. So the second factor is going to be pressure and volume. So remember, volume and pressure of a gas are always inversely related. We have this nifty equation, P1 multiplied by V1 equals P2 multiplied by V2. So the equilibrium will shift in the direction to balance out the pressure or the volume. So it will move in a direction that will either increase or decrease the total moles of gas. And moles is a scientific term. It's a specific amount of gas. So increases in temperature or in pressure or decrease in volume will cause the equilibrium to shift towards the side of the reaction with the fewer moles of gas, and vice versa. So we're going to do an example of that right now. So if the volume is suddenly decreased or the pressure is increased, the new equilibrium is going to shift toward the products because it has less moles, and moles just meaning we have a 2 right here, so that's 2 moles of gas on the product side, and on the reactant side we have 3, and then since this one has nothing in front of it, but we know that there's an N here, this is a 1, it's an invisible 1, so we have 4 moles of gas on this side and 2 moles on this side. And since we're increasing the pressure of the gas, we're going to shift toward the side that has less moles, which in this case ends up being the product side. So temperature is our final factor that's going to affect the equilibrium. So the effective temperature depends on whether the reaction is exothermic or endothermic. So exothermic reactions, think of a heat as being a product. So for example, if this is our equation right here, think if it's exothermic, if we know that it's exothermic, think about heat as being a product because we're giving off heat. Exo, heat is exiting, so heat is going to be a product here. So an increase in temperature means that we're adding more heat, and to kind of shift to reduce this change or to maintain equilibrium, our equation is going to shift more toward the reactants. This is kind of the opposite thing happens for endothermic reactions. So with endothermic reactions, think of heat as a reactant. So endo, we're entering. So heat is entering. So heat is the reactant here. So an increase in temperature will shift the position of equilibrium toward the products. So if we're adding heat to an endothermic reaction, then that means that we're adding heat as a product, and that to balance this out, our equilibrium is naturally going to shift us toward the product. So we're adding heat as a reactant, we're shifting toward the product, because so cooling has an opposite effect on equilibrium. So it's toward the side that heat is on. So if we're cooling something, that means we're taking heat away. So we're going to shift more toward the side that the heat is on in order to balance out our reactions. So now that you have the notes, you guys feel free to pause me, rewind as needed. You guys are going to fill out this last page on page 10. So it's kind of practice about how equilibrium changes based on those 3 factors that we talked about. So you guys have these 3 factors. So if pressure is increased for this specific reaction, so it's an exothermic reaction, remember that. So if pressure is increased, then how is equilibrium going to change? So is equilibrium going to shift toward the products or toward the reactants? Use your notes for this. We'll go over this tomorrow in our live classroom. Okay, so you guys should have page 10 completed. So take a minute, pause me now, take 10 minutes, take 5 minutes, however long you need, pause me now to complete this. So you're telling me how equilibrium is either going to shift to the left or to the right based on the scenario that it gives you for this specific reaction. So pause me now to do that. Okay, welcome back. So by now you guys should have completed this last page on page 10. So you should be all done for today, Wednesday, April 1st. So good job with that. We are going to go over this tomorrow in our online live classroom. So in our Google Hangout, that's what I'm going to do, and I'll record it. So you guys, those of you who can't make it, I'll put it on YouTube. So just to look ahead, we are going to be continuing talking about how reaction rate is changing for in different scenarios. And so we have our Google Hangout tomorrow. Or I'm sorry, we have our Google Hangout. Yes, we do have our Google Hangout tomorrow. I just didn't update this. So we have our Google Hangout tomorrow on April 2nd at 10:30. I'll post the link into the Google Classroom. And then we have a new upload, as always, on Friday at 10 a.m. So as always, this is my email. My phone number, please comment, text, let me know how you guys are doing. If anything's confusing, we can go over it. So I'll see you guys tomorrow.